everyone. This is the solution to the Edexcel IAL January 2020 S1 paper. So let's start with question number 1. The discrete random variable x has the following probability distribution. So this basically says that the probability of x being equal to -2 is 0.15, being equal to -1 is a, being equal to 1 is b, being equal to 3 c, and being equal to 4 is 0.15, where a, b, and c are probabilities and they're unknown, obviously. Now, the mean value of x is 1. So basically, that's the expected value of x. And the cumulative probability up to x is equal to 1. So basically, the sum of the probabilities up to x equals 1, the sum of these three, is equal to 0.63. Find the value of a, the value of b, and the value of c. So we need to find the unknowns. Now, there is one piece of information other than these two that's implicitly implied. We know that the total probability in any distribution has to be equal to 1. So the sum of the probabilities has to be equal to 1. So the sum of all these probabilities, 0.15 plus a plus b plus c plus 0.15 is equal to 1. So simplifying this, we get a plus b plus c is equal to 0.7. That will be our first equation. Now, we also have some more information. Let's first use this one just because I feel that this will be simpler, because this cumulative probability is the sum of these three. So that's two unknowns right there. However, the expected value probably has all three of the unknowns. So since this is simpler, let's do that one first. Now, the sum of the three probabilities up to x equals 1, that's going to be equal to 0.63. So 0.15 plus a plus b is equal to 0.63, and from here we get a plus b equals 0.48. Now that will be our second equation. Now, as you can see here, a plus b plus c, that's our first equation. And from here, if we subtract the second equation, a plus b equals 0.48, if we subtract that, what do we get? So a cancels out, as we can see. B also cancels out. We get c on the left, and 0.7 minus 0.48, that's 0.22 on the right. So c is equal to 0.22. Now, that's exactly what we have done here. So equation 1 minus equation 2 gives us c is equal to 0.22. Now let's use the last piece of information that we haven't yet. That's the expected value of x is equal to 1. And the formula for the expected value is just, if we look here, all that we need to do is multiply x with the corresponding probability and then add all of those up. So as you can see here, that's exactly what we have done. So minus 2 into 0.15 plus minus 1 into a plus 1 into b plus 3 into c. However, we already know c, so that's 0.22, and plus 4 into 0.15, that's that. Now this is equal to 1, and if we simplify this, we get minus a plus b is equal to 0.04. That's our third equation. Now, if we remember, our second equation was a plus b equals 0.48, and our third equation is minus a plus b is equal to 0.04. If we add these, a cancels out, so we get 2b is equal to 0.52, and that gives us b is equal to 0.26. Now we can substitute this into our second or third equation. Let's go with the second one. So from here, a plus b equals 0.48, we get a is equal to 0.48 minus b. If we plug in b here, we get a is equal to 0.22. Question number 2. A group of 40 families was asked whether their family had a dog, a cat, or a rabbit as pets. So we have some information about the survey here. No family had a dog and a rabbit. 2 families had both a dog and a cat, And we have some more information here. But before reading through all this, which we need to when we solve for part A, first let's see what the events are named as. A family from this group is selected at random. D represents the event that the family has a dog, and similarly and intuitively, C is basically the family having a cat, and R is the family having a rabbit. Now, part A tells us to draw a Venn diagram to illustrate this information. So we have all this information to draw the Venn diagram, and also this one, that the total number of our universal set or our sample size is 40. Now, normally a Venn diagram with 3 events or sets inside the universal set looks something like this. So the events can, the sets can intersect with each other, and also we have this common intersection of all 3. So this is how it should look usually. However, here no family had a dog and a rabbit, so they're saying that the sets for D and R, they will not overlap. So this is how the diagram will look in our situation. So D can intersect with C, C intersects with R, but D and R do not overlap. All right, so next we have 2 families had both a dog and a cat. So D intersection R, so that's 2 right here. Then we have 12 families had a dog. So inside D, in total, it should be 12. So we have 2 here. So this is going to be 12 minus 2, that's 10. We have a 10 here. 14 families had a cat, and then we have 11 families had a rabbit. Now this is a bit interesting because we cannot actually just fill these numbers up here because these are just totals for the sets C and R. So before being able to do that, we actually need to find the value of the intersection here, just like this was given. That's why we were able to do this easily. However, we don't have this one. We need to find this first. But however, we can actually fill up something else before that. 9 families did not have any of these animals as pets. So outside all 3 sets, we have a 9 here. Now, back to what I was saying, we need to find the value of this overlap or intersection. Let's call that X. So if this is X, 14 families had a cat. So if as a whole C has 14, so there's a 2 here, there's an X here. So this is 14 minus 2 minus X, or basically 12 minus X. And also 11 families had a rabbit. So this is 11 as a whole. This is X. So this is going to be 11 minus X. Now, we know the last piece of information that we haven't used, that tells us that the sum of all the numbers here that we can see is going to be equal to 40. So 9 plus 10 plus 2 plus 12 minus X plus 11 minus X. This is going to be equal to 40. Now, let's put some brackets here. Now, we can solve for X here. It's a pretty simple algebraic equation, and that gives us X is equal to 4. So we are going to have a 4 here, and now we can fill these up pretty easily. 12 minus X, 12 minus 4 is 8, and 11 minus 4 is 7. Part B. State, giving a reason, a pair of mutually exclusive events from D, C, and R. So first, let's bring up the Venn diagram as a reference. Now, mutually exclusive events, by definition, they do not overlap. On the Venn diagram, they will not intersect or overlap. Now, as you can see, that's the case with D and R. So D and R are mutually exclusive events. Part C. Find the probability that the family has exactly 2 of these kinds of animals as pets. So, exactly 2 kinds of pets, not 1 and not even more than that, not 3. So, exactly 2. So, let's see which portions meet that criteria. So, the intersection R. So, having a dog and a cat. So, this one matches, and also having a cat and a rabbit. and only those two. So this one also matches. Now, these are the ones that meet our criteria. So what's the probability? The basic formula for probability is it's always the same. The number that meets our criteria divided by the total number or sample size in consideration. I'm saying in consideration because that will have some implications later. So I'm saying that in a subtle way. Now, but for here, we are considering basically everything. So that's our total sample, 40. So that's in the denominator. In the numerator, as you can see, we have the number that meets our criteria. So 2 plus 4. So 2 plus 4 divided by 40, that's going to be equal to 3 by 20. Part D. Showing your working clearly, determine whether or not the events D and C are independent. Now, two events being independent, that has number of equivalent conditions. So, one of them, and it's probably the most well-known one, is the probability of those two happening together, the two events. So, the probability of D intersection C is going to be equal to the probability of D multiplied by the probability of C. So the probabilities are multiplied together. So this has to be satisfied for a D and C to be independent. So is this true? Well, that's what we need to find out. So let's first evaluate both the left and the right hand sides here and see if they're equal to each other. Now, from the Venn diagram, the probability of D is just the total of D is 10 plus 2, that's 12, divided by 40, that's the total of the whole universal set. And that's the probability of D, 12 by 40. The probability of C, similarly, 2 plus 8 plus 4, that's 14 divided by 40. Now, the product of those two probabilities is 21 by 200 at its simplest. Let's see if that is equal to the probability of D intersection C. The probability of D intersection C, as you can see, D intersection C, we have 2 here. So that's 2 divided by our total, which is 40. And just for our convenience's sake, to compare it with this, let's make the denominator the same. So it's 40 here. Let's multiply both the numerator and denominator by 5. We get 10 by 200. Now, we can clearly see 21 by 200 and 10 by 200. They're definitely not equal. And since they're not, D and C are not independent. Sarah's family is in the group and her family has a pet cat. So it's already given that this family in particular has a pet cat. So the given condition is this. So given C. Part E. Find the probability that Sarah's family also has a pet rabbit. So what they need from us is the probability of R given C. So this is the probability that's required. So the probability of R given C, first let's bring up the Venn diagram. This is going to be equal to same thing as what we have done until now. Some of you might think we could use the conditional probability formula. That's fine too. However, in these sorts of problems where we have a Venn diagram that has the numbers, the portions have the numbers of the events happening, not the probabilities, it's usually much easier to just go with the regular probability formula. So what's happening here is our required number is basically R. So the number of families that have a rabbit, but it's given that we're only picking from those which already have a cat. So the number that we need is R intersection C, the number of R intersection C. And this is divided by, as you can remember, the total number sample size in consideration. Here we're only considering the families that have a pet cat. So only the number inside C, that's what counts here. So that's our sample size in this case. So if we evaluate this, the number in R intersection C, that's 4, and number in C, that's 2 plus 8 plus 4, that's 14. So 4 by 14, and we can simplify that to 2 by 7. Part F. Find the exact value of the probability of D union R given C prime. And I think you have got the hang of this. So we are again going to use our basic probability formula. So the probability of D union R given C prime is just this one and also this one happening at the same time, because this is the given event. So the number of D union R intersection with C prime divided by the sample size in consideration, which here is C prime, the number of C prime. Now, D union R intersection C prime. So inside D or R, basically all of this, this is D union R, but we are intersecting that with C prime. So outside C, so 10 and 7. So 10 plus 7, that's going to be in the numerator, and in the denominator, it's all the numbers, the sum of them that's outside C. So 10 plus 7 plus 9. We also have 9 here. So 10 plus 7 plus 9. So this is going to give us a final answer of 17 by 26. Question number 3. Sopern sells washing machines. When a customer buys a washing machine from Sopern, the customer is also invited to buy a guarantee policy to cover breakdowns and repairs for the next 3 years. The manager of Sopern believes that the relationship between the number of washing machines sold, which is M, and the number of guarantee policies sold, which is P, can be modeled by a straight line. She collected data each month for 10 months. The scatter diagram below illustrates these data. The data are summarized by the following statistics. So we have the sum of M is equal to 1124, the sum of P equals to 81, and so on and so forth. And we also have these two. The summary statistic S sub double M is equal to 6046.4, and the summary statistic S sub double P is equal to 382.9. Part A. Show that the summary statistic S sub MP, this one is equal to 1373.6. Now, first, let's note that our sample size for our total number is 10. And now, the formula for this summary statistic is the sum of M into P minus the sum of M multiplied by the sum of P divided by N. Let's put in the values that we know. The sum of MP is 32958 and minus the sum of M is 1124 multiplied by the sum of P is 281 divided by N, which is 10. And now we get the value of 1373.6 if we put this into the calculator, and that is exactly what we had to show. Part B. Find the value of the product moment correlation coefficient for these data. So the value of the product moment correlation coefficient, or abbreviated as R, that is going to be equal to the summary statistic S sub MP divided by the geometric mean. This is how I like to remember this, is you have your mixed summary statistic at the top in the numerator, and this is divided by the geometric mean, and that is basically whenever we talk about a geometric mean, that's the square root of the product of two or more things. So this is divided by the geometric mean, or the square root of the product of the pure summary statistics, the ones which only have one variable in them. Alright, so here what we get is, if we plug in all the values that we know, S sub MP was 1373.6 and divided by the square root of S sub double M was 6046.4 and S sub double P is 382.9, and we get the value of 0.903 to three significant figures. Part C. State, giving a reason, whether or not the data are consistent with the manager's belief. Now, we can see that the product moment correlation coefficient, which is a measure of the linear regression, how strong is the linear regression that is close to 1. So we have a very strong, and this is positive because R is positive here. It's plus 0.903. So we have a strong correlation. That's the most important thing, and it's positive. That's not important here. However, I just noted that. So you have a strong correlation between M and P, and that basically supports the manager's belief, which was that there should exist a linear relationship between M and P. So that supports the manager's belief. The manager noticed that the total number of washing machines sold was K times the total number of guarantee policies sold, and suggests a model of the form P is equal to 1 by K multiplied by M, or basically M by K, where K is an integer. Part D tells us to find the value of K. Now, let's see how they've defined K. That should lead us to the answer. The total number of washing machines sold. So that's the sum. This is basically the sum of M. This is going to be equal to K times, so that's K multiplied by the total number of guarantee policies sold. So that's basically the sum of P. So that's basically the sum of P. And this tells us that K is going to be equal to the sum of M divided by the sum of P. So if we evaluate this, we get the sum of M is 1124 divided by the sum of P, which is 281. And this gives us 4. Jiang works for Sopern and thought that this model oversimplified the situation and suggested that a linear regression of P on M may be more appropriate. Part E. Find the equation of the linear regression of P on M, giving your answer in the form P is equal to A plus BM, where A and B should be given to 3 significant figures. Now, in this equation, P is equal to A plus BM, we need to find these two coefficients, A and B. The first one, which we'll find is B. This is going to be equal to, now the way I remember the formula for P is basically you have your mixed summary statistic at the top divided by the pure summary statistic that's based on your independent variable. And the one that's the independent variable here, that's easy to identify, P on M. So on what? That's going to be your independent variable. Now, so this is B is equal to S sub MP divided by S sub double M, because this is our independent variable. And if we plug in the values that we know, we get 1373.6 divided by 6046.4, and this gives us 0.22717, and continue. If we round this to 3 significant figures, we get 0.227. Now, all that we need to do is find the value of A. So A is equal to the mean of your dependent variable minus B multiplied by the mean of your independent variable. You could just remember or memorize this formula. However, if you don't remember it, that is not a problem, because it's very easy to derive using the fact that by definition the regression line must pass through the point that has both the means. So basically the mean of your independent variable, suppose if it were X, it would be X bar, and the mean of your dependent variable, suppose if it were Y, it would be Y bar. Here it's M and P, so it's M bar comma P bar. So the regression line must pass through this point. So if we plug that in to this equation, basically P here now is equal to P bar, and it's going to be equal to A plus B into M. So M is now M bar. This equation must be satisfied by this point, because the line passes through that point by definition. Now, if we make A the subject here, we get A is equal to P bar minus B into M bar. All right. So this is how we got this formula. Now we can just plug in the values that we know. The means, we haven't found them yet. However, the mean of P, that's the sum of P divided by N, the mean of M, that's the sum of M divided by N. Those are pretty easy to find. So if you plug in these, so P bar is 281 divided by 10 minus B is 0.22717. The reason that I've written it like this is very deliberate. It's just to remind and say that we should actually save all intermediate values inside the calculator, so that as we're calculating new values, the percentage error doesn't increase. So we're not getting further and further away from the true value. All right, so this is multiplied by 1124 divided by 10, and this gives us a value of 2.565. Again, whatever you get here, you should save in the calculator, and this is going to be rounded to three significant figures. So 2.57, that's the value of A. Now we just plug in those into our equation. So P is equal to 2.57 plus 0.227 multiplied by M. That's our final answer. Part F. Use Jiang's model to estimate the number of guarantee policies sold when 70 washing machines were sold in a month. So basically in this question, estimate the number of guarantee policies. So we need P, and what we're given is the value of M, and well, it has been pretty obviously stated that we need to use Jiang's model. So when M is equal to 70, P is going to be equal to, in this equation, we just need to substitute M is equal to 70. And so we get a value of 2.57 plus 0.227 multiplied by 70. And that's going to be equal to 18.467. If we round this to three significant figures, we get 18.5. Now, realistically, 18.5 policies cannot be sold. A policy cannot be a half an integer. It's probably 18 policies if we were to give a realistic answer. However, we'll leave it here because in these types of questions, generally, even the decimal isn't considered a wrong answer. Usually about 70 washing machines are sold in January. Sopern decides to offer a bonus to staff during January based on the number of guarantee policies sold. If the number of guarantee policies sold is greater than the number estimated by the model, the bonus will be paid. Now, we should note the fact that they said by the model. However, the model hasn't exactly been specified, whether it's the manager's model or Jiang's model. And this is what the question is based on. State, giving your reasons, whether you would recommend that the staff use the manager's model or Jiang's model. So we already know the estimate from Jiang's model. When M is equal to 70, Jiang's model estimates that P is going to be equal to 18.5. So let's see what the manager's model estimates. So when M is equal to 70, according to the manager's model, P is going to be equal to, that's M by K. So 70 by K was 4. So this is going to be equal to 17.5, which is less than what Jiang's model predicted. Now, which one should the staff choose here? Well, the condition for getting the bonus is that the number of guarantee policies sold has to be greater than whatever number comes out of the model. So if the number from the model is smaller, then the staff is more likely to get the bonus. So 17.5 is the better value here to get the bonus. So the manager's model is the correct answer here. The staff should use the manager's model as it gives a lower estimate of P, making it easier to get the bonus. Moving on to question number 4. A researcher is studying the birth weights of babies. A random sample of 98 babies, so that's our total frequency, N, or the sum of F, was taken, and their birth weights, W kilograms, are summarized in the table below. So we have a table with the birth weights. Basically, according to the intervals or classes, we have the frequency. So suppose say the first row right here means that 16 babies had a weight between 1.50 and 2.50 kilograms. And the midpoint here for each class, we have the midpoint of that class. So 1.50 and 2.50, the midpoint of these two is obviously 2, these two endpoints. So that has been noted here. So that will be useful later. Now, a histogram is drawn to represent these data. So although not shown here or anything, so they're telling us that histogram is drawn using these data. The bar representing the birth weight 1.50 is less than or equal to W is less than 2.50. I'm going to refer these classes as W being between 1.50 and 2.50 and such, has a width of 1 centimeter and a height of 4 centimeter. Now, part A tells us to calculate the width and height of the bar representing birth weight W being between 3.50 and 4.00. All right. So, and they have given you may use these summary statistics. The sum of f into x is equal to 311.5 and the sum of f into x squared. However, information like this is usually handy when finding the mean and standard deviation, which will come up later. So for now, this isn't actually useful. So for this question, as you can see here, for one class, we know everything. For this class, from W being between 1.50 to 2.50, we know the frequency, we know the midpoint, although this is not really that useful here. And we know the width and height on the histogram that we're about to draw. We know the width and the height. However, for this class, we know nothing, and we need to find the width and the height for this bar. So on a histogram, the bar width has to be proportional to the class width. So the width here, as you can see, the class width, basically the difference between the endpoints here is 1. And that 1 centimeter, which is the bar width, has to be proportional to that. And so, as we can see here, this class has a width of 0.5. That's the class width. And so the bar width, whatever it's going to be, it has to be proportional to that. I think it's very clear to see if 1 corresponds to 1 centimeter, 0.5 should correspond to 0.5 centimeter. But formally, if we were to do this calculation, we could use proportionality. So suppose, say, we need to find the width here. So W, let that be the bar width here. That divided by the class width has to be this ratio. If we evaluate it for any other bar, has to be the same as that. So that's the rule of proportionality. So this has to be equal to the bar width of this class, which is 1 centimeter, divided by the class width of this bar, which is 1. So from here, we can get the bar width of this class 3.50 to 4. And this is going to be equal to 0.5 divided by 1 multiplied by 1 centimeter. And the final answer is 0.5 centimeter as expected. However, we are not done yet. We need to find the height of this bar. Now, for a histogram, the frequency of any bar is proportional to the area of that bar. Or in other words, the frequency is always some fixed constant, and this is fixed for the whole histogram. Some fixed constant multiplied by the area. So first, let's see what happens if we use this formula for the class that we know about. That should give us the value of k, and then we'll use that value of k for the class that we do not know the height of. So for the 1.50 to 2.50 class, what do we have? Our frequency, which is from this table, it's 16. 16 is going to be equal to k multiplied by the area of that bar. So the area is going to be the width multiplied by the height. So 1 centimeter multiplied by 4 centimeter. I'm going to exclude the centimeters here because they don't really matter at the end. So 1 multiplied by the 4, and this gives us a value of k. If we solve it, we get k is equal to 4. So now, if we use the same formula for the class that we need to find the height for, so for 3.50 to 4, we get the frequency, which is 14. The frequency is going to be equal to k. Now we know the value of k, that's 4, multiplied by the area. So the area is the width, which is 0.5, multiplied by the height, which is h, let's call that. And so this gives us a value of h, which is, we'll get 7 here, but these are all in centimeters, the actual lengths or dimensions. So h is equal to 7 centimeters. Part B. Use linear interpolation to estimate the lower quartile of the birth weights of the 98 babies. So let's bring up the table again for reference. Now, the quartiles, the position of the lower quartile, that's going to be, well, before discussing this, let's draw a very simple diagram to see why this is the case. So suppose that this is our whole data set. The quartiles are arranged like this. They basically divide the data into quarters. That's why they're called quartiles. So from the start to the 25% mark of the data, this is basically our lower quartile. 25% of the data lies here. From Q1 to basically our median, which is Q2, we have 25% more of the data. Then again, you can see the pattern. Here we have 25%, and then we have Q3 here, and then up to the end of the data, we have another 25%. All right. So the position of the lower quartile, that is why, is going to be 1/4 of the total number of the total frequency. So 1/4 of n, that's 98 by 4, and that is basically 24.5. So it's going to be the 24.5th value. Although it doesn't make sense to have 24.5 as an index, that's still accepted and used in interpolation. So this value, let's see where it would lie. So let's see, we have from the beginning up to 2.50, we have 16 values in total. And then if we go up to 3.00, we have 16 plus another 24, so 40 in total. So up to 16, obviously it's the 24.5th value. It doesn't lie in this class. However, beyond 16 and within 40, so 24.5th value, that definitely lies in this class. All right, so let's draw the diagram for interpolation. And the way we draw this is basically we put the endpoints on either side. We have what we're supposed to estimate in the middle, and the way it's arranged is on the top we have the values, basically the data values, or the weights, the values of the variables, the values of the variable itself, and on the bottom we have the corresponding cumulative frequencies. And the reason I say cumulative is because these are the total frequencies up to those values or positions. All right, so as you can see here, the endpoint, it's 2.50 to 3.00, and we have the corresponding cumulative frequencies for them. Up to 2.50, it's obviously 16, and up to 3.00, it's 16 plus 24, or 40. Now, the value that we're supposed to find, Q1, let's say it's here, and the corresponding cumulative frequency we already found, it's 24.5. And so linear interpolation, it basically says that if we take similar ratios, they should approximately be equal. And what that means is, suppose say on the top side, on the values side, let's take this gap right here. So that's Q1 minus 2.50. If we divide this by this large gap right here, this large difference right here, that's 3.00 minus 2.50. So this ratio should be approximately equal to, if we do the same thing at the bottom, if we take the same ratio with the cumulative frequencies. So here we took the small gap, so 24.5 minus 16 divided by the large gap, which is 40 minus 16. That's basically what we have done here. And we only have Q1 as an unknown here, so we can solve for Q1. That gives us 2.67 recurring here. So if we round it to three significant figures, we get 2.68. So the estimated lower quartile is 2.68 kilograms. The researcher estimated the median to be 3.14 kilograms and the upper quartile to be 3.55 kilograms. Part C. Use the median and quartiles to describe the skewness of these data. So the way we are going to compare all these values and find the skewness is we need to compare Q3 minus Q2, this difference, and Q2 minus Q1. Q2 minus Q1, this difference. And the rule is that if this one is greater than the latter, then we have a positive skew. If it's equal, it's symmetry, no skew. And if it's less than the latter, then we have a negative skew. So Q3 minus Q2, that's 3.55 minus 3.14, as you can see. And this is going to be equal to 0.41. Q2 minus Q1, that's 3.14 minus 2.68, as we have found here. And this is basically 0.46. Now, as you can see, Q3 minus Q2, this one is less than the latter, 0.46. So we have a negative skew here. Part D. Find an estimate for, so part 1 tells us to find an estimate for the mean birth weight. So let's do that first. And here we have the information that we saw before. This is where we actually need to use it. So an estimate for the mean, which is W bar, it's going to be the sum of the frequency multiplied by the midpoint for each class divided by the total number, total frequency n. So if we plug in the values that we know, we get 311.5 divided by 98, and that's going to give us 3.18 to three significant figures. So the estimated mean birth weight is equal to 3.18 kilograms. Now, part 2 of D asks us to find the standard deviation of the birth weights. So the formula for that, standard deviation is sigma, and the formula here is sigma squared, that is the variance, by the way, that's the square of the standard deviation, is equal to, and the way I like to remember this formula is it's the mean of your square, so basically the sum of f into x squared divided by your total frequency n. So the mean of your squares minus the square of your mean. And this one's pretty obvious to understand. It's the square of the mean that we previously found. So if we plug in the values that we know, the sum of f into x squared, it's given as 1051.125 divided by n, which is 98, minus our mean, which is 3.18, that's squared. And since we need to find sigma, the standard deviation, we'll take the square root here. So the standard deviation is going to be 0.78895 continued, and this rounded to three significant figures is 0.789. So our standard deviation is going to be 0.789 kilograms. Part E. Use the formula skewness equals 3 times mean minus median divided by the standard deviation to estimate a value for the skewness of these data. Give your answer to two significant figures. So there is nothing challenging here. All that we need to do is put in the values that we have found so far. So the skewness, this measure of skewness that we have here, is going to be equal to 3 multiplied by, so the mean was 3.18. The median, it was given in a part of the question, it was 3.14 divided by the standard deviation 0.789. you'd preferably save this in the calculator beforehand when you found the exact value. It's always good to do that so that we don't increase the errors in our calculations. So if we evaluate this, we get 0.152. Continue that if we round it to two significant figures, that's what this question explicitly asks us for. We get 0.15. The researcher read that birth weights should be approximately normally distributed and decides to split the class. W is between 3 and 3.5. The frequency for W is between 3 and 3.25. So it's not this class. This class has been divided as they've told us. So it's been divided into this portion and this portion. The frequency of this portion right here from 3 to 3.25 is 9. And the frequency for this class, this portion, is 23. So the first part of part F tells us to state, giving a reason, what the effect would be on the estimate of the median. Now, first, let's bring up our table and see how these changes might affect our median. Well, the median is always at halfway through the data. So the position is half of n, or n by 2, that's 98 by 2, or 49. So the median is going to be the 49th value here, and this is exactly 3.25 kilograms. Now we don't actually need to use interpolation. This is actually pretty convenient. One thing is that we should understand by the total question having 2 marks is that we wouldn't need to do something as difficult as interpolation here, and that's why it's so convenient. So if we notice from 1.5 to 2.5, if we go there, we have 16 so far. From 2.5 to 3, 24 plus 24, so we have 16 plus 24, that's 40 so far. Then from, it's not this whole class anymore with a frequency of 32. Then we have this class, which is from 3 to 3.25, which is the frequency of 9. So 40 plus 9, 49. The 49th value is exactly at the end of this class. So it's exactly 3.25. All right. So the median is now 3.25 kilograms. That's what we would get by interpolation. However, since it's exactly at the end point, we don't really need to do that. So, and it was 3.14 kilograms before. It's very easy to see that the median has increased. Part 2. Without carrying out any further calculations, state, giving a reason, what the effect of this change would be on the estimate of the mean. Now, it's very important that we note this wording over and over again when they have been saying that estimate the mean and estimate the standard deviation. The values that we found are not actually the mean and the standard deviation, because we don't know all the data values. To find a real mean or a standard deviation, we'd need every data value, the birth weights of all the 98 children individually. So we don't have that. However, given this sort of tabular data, we make an assumption that for each class, the value is the same as the midpoint. The logic behind that is the value should be evenly distributed throughout the class. So taking the midpoint as a representative should be a good estimate. However, as the question has been saying and how this method was developed, it is only an estimate. So, but that's what we need to focus on, is how this estimate came out to be. The basis for that is we consider that for each class, the value is the midpoint. So all the values in one class are exactly equal to the midpoint. That's what we are assuming here. So this was our assumption for finding the mean previously. So before, it was assumed that the weights in this class are evenly distributed. It's the same for every class, the same for this too. So we assumed that the weights here were evenly distributed, and the fact that we could take the midpoint, which is 3.25, as representative. However, now we see that the majority of the weights are in 3.25 to 3.5. So we can clearly see that after this class has been split and we got some additional data, this is clearly not an even distribution between these two. This class which has higher weights in general, it's 3.25 to 3.5. It's definitely more than this. This higher weight class has most of the data points. So even if you were to use the same method to estimate the mean, this would actually increase the mean because it would increase the sum of f into x. So that's why the mean increases.
Follow us on social media: Facebook, YouTube, Twitter, Snapchat, Instagram, and LinkedIn. So, don't be late. Enroll to your desired courses and let Bizuz be the guide to your dream grades.